Model Context Protocol security is about protecting the integration path between AI applications and the outside systems they can reach. MCP makes it easier for an AI host to connect to tools, resources, prompts, data stores, and services. That usefulness changes the security boundary. A model response is no longer only text on a screen. It may lead to a tool call, a file read, an API request, a ticket update, or another action in a real environment. At a high level, an MCP host is the AI application or environment where the user works. An MCP client is the component that speaks to an MCP server. The server exposes tools, resources, or prompts. A tool is an action the system can call. A resource is data the system can read or present. Prompt templates can shape how tasks are framed. Transports carry messages. Downstream systems are the APIs, files, databases, cloud services, and workflow platforms that ultimately provide data or perform work. MCP security is not only model security. Prompt wording can help guide behavior, but it is not a reliable security boundary. The important controls lie across application security, identity, authorization, data protection, tool governance, supply chain review, logging, monitoring, and operations. A secure design asks what the model can see, what tools it can call, which identity those calls use, what data can move, and what actions can change real systems. Useful MCP systems must be bounded, authorized, observable, and recoverable. Bounded means tools and resources have clear limits. Authorized means permissions come from policy and identity, not from model confidence. Observable means tool calls, denials, approvals, and resource access can be investigated. Recoverable means high-impact actions have rollback plans and incident response paths. The goal is not to block MCP adoption, it is to make powerful integrations safe enough to operate. Security work starts with mapping the MCP environment. The diagram should show the AI host application, MCP client, MCP servers, tools, resources, prompt templates, user identity, service identity, downstream APIs, local files, cloud services, secrets, and tokens. It should distinguish local servers from remote servers because local execution and remote service access create different risk profiles. A local server may touch files or processes on the user's machine, while a remote server may rely on network trust, tenant isolation, and external service controls. A useful architecture diagram shows data flow, authority flow, and action flow. Data flow answers what information enters the model context, tool arguments, logs, resources, and downstream services. Authority flow answers which identity or token is used when a tool acts. Action flow answers what can be read, written, sent, created, deleted, approved, or changed. These flows do not always line up. A user may ask a question, the model may propose an action, and a tool may execute under a service account with broader permissions than the user expected. Trust boundaries appear between user input, model output, tool metadata, tool execution, external content, and downstream systems. User input is not automatically safe. Model output is not automatically authorized. Tool descriptions are not neutral. They influence how the model thinks about tool use. External resources may contain stale, misleading, or hostile instructions. Downstream systems may enforce their own policies, but the MCP application still decides what to request and what context to expose. Architecture visibility prevents vague risk discussions. Instead of saying an agent can use tools, the team can say which host connects to which servers, which tools are available, which resources are exposed, which credentials are used, and where approvals happen. That clarity supports least privilege, monitoring, incident response, and governance. Without it, teams end up trusting the model, the tool, the server, and the user interface as one blended boundary, which is exactly what MCP security needs to avoid. Threat modeling an MCP system means separating the instruction path, the data path, and the action path. The instruction path includes user prompts, system instructions, tool descriptions, prompt templates, and external content that may influence model behavior. The data path includes resources, files, retrieval results, tool responses, logs, and downstream records. The action path includes tool calls that can read, write, send, modify, approve, or trigger activity in other systems. Prompt injection is a high-level risk where untrusted instructions influence model behavior in a way the system did not intend. Indirect prompt injection is especially relevant because the model may read external content from documents, tickets, web pages, emails, repositories, or resources exposed through MCP. The training point is not to memorize payloads. The stable lesson is that external content should be treated as data with provenance and policy, not as trusted instructions that can override application rules. Tool metadata can also create risk. A malicious or misleading tool description may shape when the model chooses a tool or what arguments it sends. Overbroad permissions can turn a narrow task into broad access. Confused deputy risk appears when a component with legitimate authority is tricked into using that authority for an unintended purpose. Supply chain risk appears when a server, dependency, package, or installation path is trusted without enough review. A practical MCP threat model asks 3 blunt questions. What can the agent read? What can it call? And what can it change? Then it tests the answers against misuse scenarios such as data leakage, unauthorized actions, stale or untrusted resources, malicious server registration, overtrusting model output, and approval bypass. The resulting controls should live outside the model. Authorization checks, allow lists, validation, approvals, isolation, logging, and incident response. Identity is one of the most important design choices in an MCP system. A user may ask for an action, the AI host may decide how to assist, an MCP server may expose the tool, and a downstream API may enforce permissions. Those layers should not be collapsed into one vague identity. User authorization is different from application authorization. A service account is different from a delegated user token. A model-generated request is different from verified user intent. Delegated access lets an application act on behalf of a user within defined limits. OAuth-style concepts such as scopes, audience, token lifetime, and consent are useful mental models even when the exact implementation varies. Scope should describe what an integration can do. Audience should constrain where a token can be used. Consent should make the user or administrator aware of meaningful access. Token lifetime should limit exposure if credentials are mishandled. Careless token pass-through can blur trust boundaries. If a powerful user token is passed through multiple components, tools, or servers without clear policy, components may gain access they do not need and users may not understand what is being authorized. Safer designs separate user intent from model-generated action requests, issue narrowly scoped credentials where possible, keep secrets out of prompts and logs, and enforce authorization at the application or service boundary. MCP tools should not gain permission merely because a model asks for them. The model can propose an action, but policy must decide whether the action is allowed. High-impact actions should require explicit consent or approval. Permission checks should consider the user, the tool, the resource, the requested operation, the data sensitivity, and the current context. Consent is not a decorative prompt. It is a control that helps connect user intent to authorized action. MCP tools should be treated like software integrations with permissions, owners, and risk ratings. A tool inventory should record what each tool does, who owns it, what server exposes it, what permissions it requires, what downstream systems it reaches, what data it can access, and whether it is read-only or write-capable. A server inventory should capture provenance, installation source, maintainer, dependencies, version, approval status, and whether the server is trusted for the current environment. Trusted and untrusted servers should not receive the same treatment. A locally reviewed internal server that exposes narrow read-only queries is different from an unknown server installed from an unreviewed source. Remote servers also introduce transport, authentication, tenant isolation, and service availability considerations. Local servers may introduce file access, command execution, process access, or workstation data exposure. Both models can be useful, but both need governance. Tool descriptions are security-relevant metadata. They may guide the model's decision about when and how to call a tool. Descriptions should be reviewed for accuracy, scope, unsafe language, hidden assumptions, and mismatch between advertised behavior and actual permissions. Allow listing can limit which tools or operations are available in a given context. Version pinning and dependency review can reduce supply chain drift. Disabling unused tools reduces the attack surface. Operational controls should match tool risk. Low-risk read-only lookup tools may need standard logging and authorization. Write-capable tools may need argument validation, approval gates, rate limits, transaction previews, dry run modes, and rollback planning. Tools that touch local files, cloud resources, email, code repositories, tickets, or production systems deserve stronger review. The security habit is to ask what authority the tool carries, not just what friendly name appears in the client. MCP systems can move sensitive data through prompts, resources, files, logs, retrieval results, tool responses, and downstream APIs. That makes data protection a first-class design concern. A model context may include customer records, internal documents, code, tickets, telemetry, credentials, regulated information, or personal data. The fact that the data is being used to help the user does not remove the need for access control, minimization, retention limits, and monitoring. Resource access should be governed by application policy and identity, not by model confidence. If a user is not allowed to read a document, the model should not receive that document because it seems useful. Per-user access filtering, tenant isolation, group membership checks, and resource-level permissions should happen before content enters the model context. Cross-user or cross-tenant leakage is a severe failure because the model may summarize, combine, or expose information that never should have been available. Resource provenance helps teams reason about trust. The system should know where content came from when it was retrieved, which identity accessed it, and whether it is authoritative for the current task. Stale or untrusted resources should not silently drive high-impact actions. Redaction can reduce exposure when full content is unnecessary. Data minimization asks whether the model needs the whole file, a small excerpt, metadata, or a structured result from a server-side query. Secrets handling deserves special care. Tokens, credentials, private keys, session cookies, and connection strings should not be placed in prompts, tool descriptions, or logs. Local file access should be constrained to intended paths and operations. Cloud resource access should use least privilege and server-side policy. Encryption, retention controls, and logging hygiene matter, but they do not replace authorization. MCP data protection works best when sensitive content is filtered before it reaches the model. Tool execution controls are where MCP security becomes operational. Read-only tools and write-capable tools carry different risk. A read-only inventory query may expose sensitive data if poorly controlled, but a write-capable tool can modify files, send messages, create tickets, change cloud resources, update repositories, or trigger workflows. High-impact actions should never rely on the model alone to decide what is safe. Command execution, file modification, email, messaging, code repository changes, cloud actions, ticketing, and workflow automation all need external enforcement. The model can produce arguments or recommend an action, but validation should happen in deterministic code. Schema validation checks shape and type. Argument validation checks allowed values and constraints. Allow-listed operations limit what the tool can do. Policy checks decide whether this user, in this context, can request this operation. Transaction previews and dry run modes help users understand consequences before execution. A preview can show what file will change, which ticket will be updated, who will receive a message, what cloud resource will be modified, or which repository branch is affected. Human approval gates are especially important for irreversible, costly, external, or privileged actions. Approval should be tied to the specific action and arguments, not just to a generic permission granted earlier. Rollback planning completes the control story. If a tool can make changes, the team should know how to undo or contain mistakes. That may involve version history, reversible workflows, backups, change records, rate limits, or incident response procedures. Safe operations assume that models can misunderstand context and users can approve too quickly. The system should make the safe path easy and enforce hard limits outside the model. MCP audit trails should make tool-mediated activity understandable. Useful logs include tool calls, selected server, calling user, application identity, authorization decision, approval record, resource access event, policy denial, server connection event, error, timing, and outcome. For high-impact actions, logs should preserve enough context to reconstruct who requested the action, what was approved, what arguments were used, and what downstream system responded. Monitoring should look for unusual tool usage, suspicious server behavior, data access anomalies, repeated denials, unexpected local file access, unusual API calls, elevated error rates, approval bypass attempts, or activity outside normal patterns. The goal is not to drown teams in model transcripts. The goal is to expose the security-relevant events that show whether tools and resources are being used according to policy. Logs also create privacy and security risk if they store too much. They should avoid unnecessary secrets, tokens, credentials, regulated data, personal information, and sensitive user content. Correlation ID, resource identifiers, tool names, policy outcomes, and carefully scoped summaries can often support investigation without storing full prompts or full resource contents. Logging design should be intentional because incident response is harder when logs are either empty or dangerously over-collected. Incident response plans should cover unauthorized actions, data leakage, tool poisoning, malicious server activity, policy bypass, approval confusion, and suspicious resource access. Responders need to know how to disable a tool, revoke a token, block a server, preserve evidence, identify affected users or tenants, review downstream actions, and communicate impact. MCP security is strongest when monitoring and response are designed before the first serious incident. MCP security protects the full integration path between AI applications, users, tools, resources, servers, identities, secrets, and downstream systems. The security boundary changes because AI-assisted behavior can discover resources, call tools, and influence real systems. A model answer is no longer just a paragraph. It may be connected to actions and data flows that require application security, identity, operations, and governance controls. Strong MCP security starts with architecture visibility and trust boundaries. Teams should map data flow, authority flow, and action flow. They should identify hosts, clients, servers, tools, resources, prompts, users, service identities, secrets, local files, cloud services, and downstream APIs. That map gives the organization a shared view of what the agent can read, what it can call, and what it can change. Prompt wording alone is not a reliable security boundary. Authorization, least privilege, consent, tool allow listing, server improvements, argument validation, resource filtering, tenant isolation, approval gates, logging, and monitoring must be enforced outside the model. Tool descriptions and external content should be treated as security-relevant inputs, not automatically trusted instructions. Data minimization and secrets handling help prevent sensitive information from entering places it does not belong. The goal is controlled adoption. MCP can make AI applications more useful, but useful systems need governance, recoverability, and incident response. Treat tools like integrations, servers like supply chain dependencies, resources like governed data, and model-generated actions like requests that require policy enforcement. Done well, MCP becomes auditable, privacy-aware and aligned with organizational risk decisions instead of being an uncontrolled bridge between a model and production systems.